Hey guys, this is problem 1 for tutorial 2. So for the problems in this set, if you're given numerical solutions in parentheses here, these are not meant for you to just use. You're supposed to derive these yourself and check your work with these. The idea is that if you don't get these values, these are your reactions. If you don't get the right reactions, then the rest of your results are going to be completely off, and it's not going to be beneficial for you to finish the homework. So try to make sure you get at least 3 actions right, then you'll be on the right track. And you notice you have these weird fractional values. That is because this is not just the sum of forces equation. This is not just a simple structure that you can analyze. You have to do you have to incorporate an extra equation in there. So let's start. You're actually looking for the reactions here, which are technically kind of given, but you need to derive these yourself. You're looking for the axial forces and the truss members. So this half of the structure is a truss, and the other half of the structure is a beam. The member forces in a beam are the shear and moment diagrams. So you need to find what, or the shear moment equations also. You need to find the equations and preferably also draw diagrams for this member. Okay, now let's get started. You'll notice that right away we have 2 pin connections here, and that is actually a problem. You normally only see pin or rollers, and what does this mean? This means that if we were to treat it like a rigid body, for example, let's look at the case where we have something just like this. We have four unknowns, right? We do not have enough equations in order to solve this. This is where that hinge comes into play. We have a hinge here. This will provide us with an extra equation known as an equation of condition. If I apply a hinge here, now I have my, so this was 4 unknowns. Originally I only had 3 equations. I had sum of forces in the x, sum of forces in the y, and sum of forces in the z. Now sum of moments about z. Now I also have sum of moments about the hinge equals 0. And this hinge, the moment about the hinge, is separate than the moment about z. If I take the moment about any point on here, that's taking the moment about z. If I take the moment at the hinge, that's taking the moment at the hinge. So I have 2 separate equations, even though they look quite similar. Okay. So now let's get started. When we do our sum of forces in the x direction, we look at the entire structure. Actually, for all of these, we can look at the entire structure. And what do I mean by that? If I start here, I would do sum of forces in the a. So I would have a vertical force here, horizontal force here. I would have a vertical force here, a horizontal force here. I would call this let's call this gx. Gy, ax, ay. I have those 4 forces. I can do sum of forces in the x direction very easily, right? I have, and it's hard for me to show this on here and write at the same time, but let's try doing this. I don't know if you can see it through that. That's fine. I'll just pull this aside and start writing. You should have this in front of you when we're going over this, but sum of forces in the y is going to be ay plus gy plus 20 root 2 over 2. And I'm going to, instead of calling this 20, I'm going to call this 2p, because by putting numbers in here, I kind of obscure what I'm doing. So I think it'll be better for you if I keep track of what my loads are and what my lengths are rather than reducing them down to a single number. I know that'll annoy some people, but I think it'll be more beneficial in the long run. In the x direction, I have ax plus gx plus 10, or plus p, plus 2p root 2 over 2. And if I do the same thing for moments about a point. For example, let's assume that I do a moment about point A. I would write out those equations. For moment about the hinge, What's interesting about moment about the hinge is that I could actually split this into two separate components. I could look at just this half, or I could look at just this half. And what do I mean by that? What I mean is, if I just look at this half and I say moment about the hinge has to be equal to 0, then when I take moments about here, like everything will sum to 0. Something over here, everything will sum to 0. If I combine these two things, if I look at this and I say, well, I'll take the moment about E and look at all the forces, I'll get the same thing. I'll get m equals the sum moment will be equal to 0. Right? Let me try and say let's say this in a different way. What I'm trying to say is, if you look at the moment about the hinge left, is going to be equal to the moment about the hinge on the right is going to be equal to the moment about the hinge total is going to be equal to 0. And you can try this if you like when you get your final results, or you can even try it now with these results. But what I'm saying is, for this moment equation about the hinge, I only need to look at this half or this half. I don't need to look at the whole structure. When I do moment about some point, I do need to look at the whole structure. When I'm looking at moment about the hinge, a hinge connects 2 or more components. I only need to look at one of those components at a time. Here I have 2 components. I only need to look at one component or the other at a time when I'm using this equation. So for example, my moment about the hinge right equation sorry, I use a bad marker. Moment about right is going to be equal to 20 times 4 root 2, and let's say that this is positive. Sorry, this is 2p. Plus 8gy minus, or plus, sorry, 8gx. I have moment due to this force, due to this force, and due to this force. I don't need to look at these forces. I only need to look at one side or the other. Again, this is only for moment about the hinge. So that's how you get your reactions. You now have 4 equations. You have 4 equations. You get your four unknowns. Okay, now to get the forces in the truss member, you can either use method of sections or method of joints. For method of sections, method of sections is basically I put a line through the structure, and then I look at the section that I cut off, and I analyze that separately. So if I look at this section, I have something that looks like this. I have something that looks like that. And this should be a continuous line, but my drawings are terrible. This would be FBD, FCD, FCE. Now I'm interested in the moment in every force, or the force in every member. So I would need to cut through every single member in order to use method of sections by itself. I'd have to make one cut here, I'd have to make one cut here, I'd have to make one cut here, I'd have to make one cut here. I'd have to somehow cut through every single section, I'd have to cut through every single member at least once in order to figure out what that member force is. So in this case, method of sections may not be very useful. We do have another method. Oh, sorry. I should note this gives you 3 equations. We have sum of forces in the x, sum of forces in the y, and sum of moments about some point. Again, these must all equal 0. We have 3 equations, therefore we can solve up to 3 unknowns simultaneously. So if I have to cut more than 3 members, method of sections is going to be tedious to use. Let's try method of joints. So this is sections. Method of joints, I can look at any joint on here, and I just draw what the forces should be. So again, for this one, sorry, I should have drawn arrows here. I like to draw my members all in tension, which is one way of saying, like, draw all your arrows going away from the points. I'll show you what I mean here. If I look at joint A has 4 forces going into it, right? I have AC, AB, AX, and AY. Let me draw those out really quickly. I have the 2 reactions. I have AC, and I have AB. This is A. I have the reactions, AY and AX. Notice that I only have 2 unknowns here. I know what AY and AX are. I found them at the very beginning. I only have 2 unknowns here, so I can method of joints. You get 2 equations per joint. So I can solve 2 unknowns simultaneously with method of joints. I have 4 values here, but only 2 of them are unknown. So when I do sum of forces in the x direction equals 0 and sum of forces in the y direction equals 0, I'm going to be able to solve AB and AC. The nice thing about method of joints for this problem is that once I solve this one, I know what this one is, and I know what this one is. If I look at point B now, I have 2 unknowns again, right? I have BD and BC is known, AB is known. I have 2 unknowns, 2 equations, so I can solve for this directly using method of joints. I get these 2. If I look at joint C now, I have 2 unknowns again, because I know what BC is and I know what AC is. I have to find, if I use method of joints, I have 2 equations, 2 unknowns. I can solve for CD and CE. And then once I get up to here, I can just solve for DE directly. So the nice thing about method of joints is that you kind of work your way through the entire truss. Method of sections requires you to be very careful. Method of sections is useful if you're looking for a specific member force, but if you're trying to find all of them, it's usually preferable to do method of joints. Okay, now we get to identify their tension or compression. These arrows assume tension positive. The way I drew my things here. So I normally assume that tension is positive. For some reason, it's just easier for me to work with that assumption. I don't like my arrows going all into the same point. It's easier for me to imagine that the forces are pulling on each other rather than pushing on each other. But if you work under the assumption that everything is in tension positive, then any negative values you get in here will be compression. So basically, if you use the same notation I did, positive will be tension and negative will be compression. If you use the opposite case, if you assume, for example, that AB, AC are going this way, these will be in compression. These will be compression forces, and positive for these forces, these arrows, these directions, arrows going into the point will be compression, and negative values will be tension. So think about that carefully again. I have arrows going away from here. My values are all in tension positive. Arrows coming in, compression positive. Okay, so that is that. The beam. This beam member, it might look a little intimidating because it's on a slope, but the way of looking at it is just like this. If I turn it this way, then it's just a beam with a point load on it. Now, when I look at member forces at E, I'm going to have force DE coming in this way, and I'm going to have, sorry, I'll just call this DE, and I have CE coming in here. And again, I should draw these arrows the other way. I should keep my signs consistent. I'm sorry, I'm going to do that part again. I should have D and CE here. I'm gonna, my E is at an angle. Rather than trying to find out like what the horizontal and vertical components are of this, why don't I just assume that I have something in the same direction as this? Why don't I assume, and I'm using red here because this is an important concept for you to know, why don't I just assume that I have my x-axis going this way? And I'll call this x prime, and I have a y prime axis going this way. And if I do that, then when I come back over here, I'm going to have to find out, I'll call this axial. I'll call this shear. And I can do this. Yeah, I can do this quite well, right? Or without any problems. I want to find out, it doesn't normally matter, normally I'm working with the x and the y directions, but in this case I could just pretend that I have something like this, right, where this is my x and this is my y, and these two are at angles, at weird angles. And so like how would this work in practice? Well, these two should actually be parallel. These two should be, this should be parallel. The y prime is perpendicular to this axis, but I believe that is parallel. No, it's not. This is 45, 45. No, this is, it should be 90. I think these should be parallel. I think they should be parallel like this. Yeah, because you go across 2 and you go up 2. So that is fine. But to actually do this, I'm going to break this DE into a axial component and a shear component. And this GE is already in the direction of shear. So if I do shear, this DE up here should be DE cosine theta. DE sine theta. And again, cosine theta and sine theta should be the same in this case. They should both be 45 degrees, so it should be the same either way. When I do that, I get sum of forces in the x prime direction is equal to shear minus CE minus DE cosine theta. Right. So I hope I'm not confusing anyone with what I'm doing here. What I did was I'm basically changing my coordinate system. Instead of having x horizontal and y vertical, I am rotating it slightly. So you might have seen something that looks like this before. I'm just rotating my coordinate system a little bit just to make the problem easier. If that bothers you for whatever reason, you have the reactions here, right? You can do the same thing at G. If I'm doing in G, let's make x positive going that way. I'll call it x double prime. And y double prime going positive that way. And if you note, as long as you note your notation, this might be easier for you to visualize because you don't have to deal with the fact that there's a hinge here. But I have this force gy coming in at an angle to my x prime and y prime axes. So I need to find the components of this in this direction and this direction. I need to find the components of this in this direction and this direction. Sorry, in this direction. Okay, so that is the main concept. If I do something like this, the reason why I'm doing it this way is because then I can work with a horizontal beam. Then I can look at my beam, and let's say that I work with from point G. I make my cut this way. I have this is some value x. I have my beam here. This is 20 kilonewtons. And I have a force, gy prime, double prime, and I have some force here, gx double prime. Right, these are the forces that I got by rotating my system a little bit. I have a point load here, so I need to do a piecewise equation. I need to make one cut here. I need to make one cut here. This is x less than 4√2. This is x greater than 4√2. You'll get 4√2 based on the geometry. Yeah, so when I do when I look at the first cut, here's black. I'll trying to keep this consistent. The first cut, I have shear, moment, and axial. This is my v of x, m of x, a of x. A of x will be equal to g of x prime. Note that there's no function of x here. This is a constant. A of x is not changing along the entire length of the beam. My v of x will equal to gy, my v of x, if I do sum of forces in the y, if I do sum of forces in the x, I get a of x plus gx prime equals 0, so a of x equals negative gx prime. If I do sum of forces in the y, I get v of x plus gy prime double prime equals 0. So v of x equals negative gy double prime. Note how the sign changes here. I'm adding two positive terms together and setting them equal to 0. So one of them has to change signs. My moment about z, let's do this way positive. It's going to be m of x minus gy prime times x. Right, this is the distance x. I don't know how far I am. I could be here, 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 here. I'm some distance away x from the reaction. I'm some distance x. I'm just between the reaction and the load. I'm somewhere in this line. So I know that this has to be, I had to multiply this force by x. I set this equal to 0 equals gy prime of x. No negative sign here. And I just do the same thing after the cut. So these are all for x less than 4√2. For x greater than 4√2. I do the same thing, but I look at now including this force here. So now this distance, or the distance to this load, is going to be x minus 4√2. And I hope this is clear for everyone. When I look at the shear here, I'm interested in the my v of x is going to be equal to v of x plus 20 plus gy double prime equals 0. V of x equals negative 20 minus gy double prime. This is constant. My m of x is going to be equal to 20, which is the force, times x minus 4 root 2, which is the distance between this point and this load. Sorry, I should do minus here. M of x, if I'm doing this way positive, m of x is positive, minus something that's going this way, minus gy double prime x equals 0. So x minus 4 root 2, so this will be positive now, plus gy double prime x. Okay, so yeah, you still need to, so your job is going to be to find out what these reactions are. Your job is going to be, I basically did most of this problem for you. Your only jobs are to now actually solve for these forces. I think I gave you the forces in the beam. I gave you the shear moment in the beam, if you've been following this carefully. Make sure you can actually do this yourself. It's perfectly fine, or not perfectly fine, but I mean, if it's, you can get a good score on the homework by just copying what I have here, but if you don't understand what's actually going on, then we'll tell very easily on the exam. So make sure you understand what is happening here. I went over this problem in depth because I really want to make sure you guys understand what like the change in coordinate system is, but yeah. So I know this video was long, but hopefully it was useful.